Hello students, welcome to the class. So today we'll see the theory part 6 of the chapter Thermodynamics, in which we will cover the section 5.4 of the NCERT. So this is the disclaimer. Now, in this lecture, our objective would be to look for the standard states of H. So we have different definitions for enthalpy of reaction in different conditions. We will look upon that and we will try to calculate the enthalpy change for those reactions. Then we will look at a very important law, which is called as Hess's law of constant heat summation. We'll try to understand it as well as apply it on a given example. If I specifically talk about the NCERT topics that we are going to cover, according to that, we are covering the section 5.4, which is enthalpy change in a delta RH for a reaction, that is known as reaction enthalpy. Then in that, we'll see the standard enthalpy of reactions, enthalpy change during phase transformation. So this is your first type of process that we will cover in terms of enthalpy. After that, we will look at the standard enthalpy of formation. So this is the second type. So this is the most important part, which is thermochemical equations. Okay. So all of this enthalpy change during phase transformation, during the formation, during the reaction, all the enthalpy changes can be expressed along with the reaction with the help of a very important equation known as the thermochemical equation. We will talk about in detail that what are the specificities we need to mention, what are the conventions that we need to follow. After that, we will look upon the Hess's law of constant heat summation, which is just a algebraic play of this thermochemical equation. So let us begin our discussion with the reaction enthalpy. So what is reaction enthalpy? It's very simple. During a reaction, the enthalpy change that is occurring or the heat change that is occurring at constant pressure is known as the enthalpy. Now, why I have used the term heat change at constant pressure? Because we know that QP is nothing but our enthalpy. So in that sense, your enthalpy is very, very important because enthalpy is what? It is the heat change at constant pressure, and most of the reaction that we do it at constant pressure, that is atmospheric pressure. So we can calculate the heat change that is occurring in the reaction if we know the enthalpy. Now, how do we represent it? Very simple. Just put a subscript between the delta and H, and it will be your representation for the enthalpy change. What are the methods of calculation? So we simply sum up the enthalpies of product, okay, minus the enthalpies of reactant, and that will give you the enthalpy of the reaction. Remember, you need to multiply the coefficient for each and every product along with the given enthalpies or individual enthalpies, and that too is same for both products and reactant. So the multiplication of the coefficient is that part which students often miss during the calculation. So keep this in mind. Now the question arises, why are we multiplying with the coefficient? To answer that, we have to go back to our basics, according to which our enthalpy is an extensive property. So if you are defining it, you have to define it according to the equation, according to the number of moles that are involved. Okay, because it will change upon changing the number of moles. Because number of moles is deciding the substance amount, and substance amount is directly related to the extensive properties. What are the H product and H reactant here? So H product stand for the enthalpies of the product, okay, and AI and BI are the stoichiometric coefficient. Then here is a symbol which is used, and it will be used in many of your formulas if you see in your NCERT textbook, and that symbol is sigma. Now you don't have to worry about it. It's a very simple notation, and it is just there to explain the summation or to represent the summation. Okay, so suppose you are to be counting the total marks of the students that you got in your chemistry exam. How we will do it? We'll simply represent it with a summation sign. Okay, so it is simply a addition and nothing else. Next, Can we do it with the help of example? Yes. Let us take an example, which is combustion of methane. Now, combustion of methane will produce carbon dioxide and water, and that is true for all hydrocarbon. You just have to change the coefficient for different hydrocarbon. Now, during the combustion, the methane will react with oxygen. And if you want to calculate the enthalpy change for the same, how do we calculate it? We take the enthalpies of the product minus the enthalpies of the reactant, with each multiplied with their coefficient. Suppose in this reaction, what will be the product? It will be carbon dioxide and water. So the enthalpy of the carbon dioxide multiplied with 1. Now the important part is that we are taking HM. In the formula, if you see, we are simply writing H product and not putting any specification on it. But in your questions, you will generally notice that you are taking the molar enthalpy. Therefore, we have written it as HM, which is representing a molar enthalpy of the carbon dioxide. Now this is multiplied with 1 because carbon dioxide has a coefficient of 1 in the balanced chemical equation, if you see. What about water? So water has coefficient as 2. So we have to multiply the molar enthalpy of water, of the liquid water, with 2. So this is total for the product part. Just enclose it in a square bracket minus. In the next part, we will write it for the reactant. Now again, the methane is having a coefficient of 1. So you don't need to multiply it with anything. Simply write the molar enthalpy of methane and add it with the double of the molar enthalpy of oxygen. Why we are doubling it? Because oxygen again has a coefficient of 2. Now, we are talking about the coefficient. I'm not talking about the 2 that is written in the subscript. Okay. That is for the coefficient that is written on the left side of the oxygen. I hope you now know that how to apply the formula for the reaction enthalpy calculation if you know the enthalpy of the product and the enthalpy of the reactant. Here I am putting a very important and a crucial point here. So this is not the only formula that you use. There are many formulas in terms of different enthalpies that are used to calculate the enthalpy of reaction, and we will see them. Then our first type that we will discuss is the standard enthalpy of reaction. Now this is just an extension for the enthalpy of reaction. How? So in standard enthalpy of reaction, we are simply calculating the enthalpy of reaction, but the substances that are involved in the reaction are in their standard states. How? So basically, what we do, we keep our substance at 1 bar pressure. And whatever the state that we observe at a given temperature. Now the temperature is not fixed here. Okay, we are only keeping the pressure constant. That is 1 bar if you are taking the standard condition. How do we represent it? We use a notation which is not. Okay, now you can use 2 types of notation here. You can simply use a circle above the H, or you can use this crossed circle. In most of the cases, you will observe a simple circle. Okay, you can use that. There is no issue in that. Let us try to understand the same with the help of an example. Suppose we are looking at the liquid ethanol and we are observing it at 298 Kelvin and at 1 bar pressure. So the temperature that we are specifying here in this case specifically is 298 Kelvin. Now it is seen that at 298 Kelvin and 1 bar pressure, the ethanol is present in the liquid state. Clear? So we will take the liquid state of the ethanol at 1 bar and 298 Kelvin. Next, if you could consider it for the iron, you can now change the temperature. So this is the important part, right? So here if you see, although it is a standard, but we are standardizing this thing at a different temperature. So temperature is never fixed. It is given as 500 Kelvin. But the pressure is fixed, it has 1 bar. And here the iron is presented as solid iron. Okay, so in this way we represent the standard condition. Got it? Now if this is clear, let us move on to enthalpy changes during phase transformation. So this is very, very important for you. For that, you have to first see that what is phase transformation. So it is a process in which there is a change in energy. And what is that process? So this is simply the conversion of states from solid to liquid, liquid to solid, solid to gas, and so on. So solid is a phase, liquid is a phase. So we are just what we are doing? We are changing the phase from solid to liquid, liquid to gas, gas to liquid, liquid to solid. So many possibilities are there. Now in this processes, if you observe, then you can see that the processes involve the exchange of heat. The solid requires heat for converting it into liquid, and liquid further requires more amount of heat to be getting converted into gas. If you want to go in the reverse way, you have to lower the temperature. There is one more possibility. You can directly go from solid to gas. There is no issue in it. So here I am just representing your energy change. Now in your phase transformation, various types of transformations are possible. We will try to define the enthalpy change for each of this. The first one is the enthalpy change for fusion, which is simply the conversion of solid into liquid. In that case, whatever the heat is being exchanged at constant pressure at a standard condition is known as your standard enthalpy of fusion or molar enthalpy of fusion, represented by delta fuse H naught. Next we have for the vaporization process, in which the liquid is getting converted into gas, and in that case we are writing it as standard enthalpy of vaporization or molar enthalpy of vaporization. Another phase transformation is somewhat crucial and not according to the normal convention that we see. So it is observed for some specific substances, in which those substances get converted into gases directly from the solid phase. You can take the example of camphor, right? For those conditions, we have the standard enthalpy of sublimation. Now we'll try to understand each of this with the help of specific example. So let's see. First one is the standard enthalpy of fusion. What is the standard enthalpy of fusion? So two things are important here. First is we need to maintain the temperature at a given specified temperature. So that temperature will be according to the process. Okay, we will not specify it by ourselves. Got it? Now if I talk about the number of moles, so the number of moles is fixed. It is 1 mole. So the enthalpy change for the conversion of 1 mole of solid into liquid by melting process is called as the standard enthalpy of fusion. Here you have to keep the pressure also at 1 bar. So this is also mandatory. Now, how do we represent it? We have seen it. It is delta fuse H naught. Now let us take an example. Suppose we are converting the solid water into the liquid water. During this process, the enthalpy change for 1 mole of water to be converted into the liquid phase from solid at 1 bar pressure is 6 kilojoule per mole. Got it? So this represents your enthalpy of fusion. One very important point. If I ask you, if it is 1 bar pressure, then what should be the temperature for conversion? So all of these conversions, so I'm talking about all conversions, until and unless all conversions are not taking place completely, the solid will be at what temperature? It will be at 0 degrees Celsius. Got it? Then in this process, we know that your ice is taking up the heat. You can look at the enthalpy change value, which is positive, and simply tell that the process is endothermic. And this is a general terminology. Okay, all of your processes that involve fusion, they occur at a endothermic process. Got it? So we can write that all enthalpies of fusion are positive, making sure that you are keeping the pressure constant. So this is very, very important. And this temperature, which is 273 Kelvin for the melting of water, will change for different solids accordingly. Got it? So that is the reason we do not specify the temperature for the standard condition. Next, let us move on to the standard enthalpy of vaporization. This is the heat that is required to convert 1 mole of liquid directly into gas, and all of this will happen at 1 bar pressure. Let us try to understand this. Okay, so this is the representation, which is delta VAP H naught. Let's try to understand the same with the help of an example. Suppose we are at a constant temperature, and that temperature is the boiling point. If you are saying that pressure is standard, so that will be taken as 1 bar. So two things are there. Boiling point will be according to the liquid that we are taking, and pressure will be 1 bar. Suppose we take it for again water. So water will be converted from liquid to gaseous. Okay. And in that process, the heat that is used up by the liquid water is 40.79 kilojoule per mole. Again, it is written for 1 mole. This is very, very important. In this process, if you say that what should be the temperature for the conversion, so whole of this process will take place at 100 degrees Celsius. Got it? And the vaporization will always be a endothermic process, no matter which vaporization you are considering. Moving on further, next is the standard enthalpy of sublimation. What is the standard enthalpy of sublimation? In this, we are relating the enthalpy change for the conversion of solid directly into gas, and 1 mole of the solid is converted while keeping the pressure as 1 bar. It is represented, how it is represented? By using the term delta sub H naught. Now for you, if you are unaware about the sublimation, it is simply the conversion of solid into vapor. Okay, we know the representation now and the definition as well. So let us look at an example. We are taking the example of the carbon dioxide, solid carbon dioxide, known as the dry ice. Now this dry ice, if we take it at 195 Kelvin, this dry ice is directly converted into gas. And the enthalpy change related with the process is 25.2 kilojoule per mole, which is your standard enthalpy of sublimation. You can similarly take the example of naphthalene, and this is observed also in your clothes when you use that your naphthalene is slowly reduced to the vapor form, right? And the enthalpy change associated with the naphthalene sublimation is 73 kilojoule per mole. I hope these three transformations are clear to you. If this is clear, then let us move to the factors that affect the phase transformation. So the first factor is simply the intermolecular interaction. Greater is the strength of this intermolecular interaction between the bodies, the more heat it will require for the conversion. Then, can we take an example for it? Okay, let us take the example for water molecule. So water molecule are held together by the strong hydrogen bonds in the liquid phase. Now, if you consider acetone, then this acetone has no such kind of interaction. In acetone, we have the dipole-dipole interaction because acetone is a somewhat a polar molecule, not a strong polar one, but a weaker. So in this case, we have dipole-dipole interaction because of the electrostatic attraction between the positive and negative poles of two different acetone molecules. Now it is observed much often, and it is true also, that your dipole interaction will be smaller in strength as compared to the hydrogen bonding. Now what we can say, as the hydrogen bond is stronger in case of water, so less heat is required for the acetone case for its vaporization as compared to the water. You got it? Is it clear how the intermolecular interactions are important? Now, moving on to the next, which is very important, second very important, which is standard enthalpy of formation. What is standard enthalpy of formation? It is the enthalpy change, standard enthalpy change, if you are forming 1 mole of a substance from its constituent element, and those constituent elements should be present in the stable state, known as the reference state. Let us try to understand the same. Now, important note for you before moving further, standard enthalpy of formation is nothing but your standard enthalpy of reaction, simply. It is represented by delta F H naught. And if you consider the standard enthalpy of formation for different elements, and if those elements are present in the reference state, then in that case, you take the standard enthalpy of formation as 0. Suppose if you are taking the oxygen molecule, so oxygen is already in the standard state, which is O2, in the gaseous form. Therefore, its standard enthalpy of formation will be 0. Next, we have the standard enthalpy of formation for the carbon. Now, the standard case for the carbon is simply graphite. No other allotrope will have this formation as 0, only the graphite will have it. Next, if you consider it for the hydrogen, then the H2 case is the normal case for a hydrogen, and therefore its standard enthalpy of formation will be 0. After that, we have for bromine. Why I have written here bromine? Because most of you would think that it is a non-metal, so it will have a standard state in the gaseous phase. So it is not true. Bromine has a standard state in liquid, and therefore only for liquid bromine we have the enthalpy of formation as 0. Lastly, if you consider it for the sodium metal, suppose, then sodium is present in the elemental form. Then you will say that why are we not taking it as gaseous? Because we know it very well that sodium is a metal and it will exist as solid in the standard condition. So we will take the solid formation as 0 for the metals. I hope these points are clear to you. Now, if this is clear, let us take an example. Suppose we are seeing a formation of water, and we say that for this process, the standard enthalpy of formation will be minus 285.8 kilojoule per mole. Now, can we say it? Is it true? Can we say that the enthalpy change for the reaction is nothing but your standard enthalpy of formation for this equation? Why are we saying it? Because we said that the standard enthalpy of formation is related with the formation of 1 mole of water, and this can be seen from the equation that 1 mole of water is formed. Second thing, the species which are making up your water are hydrogen and oxygen, and we are taking those species individually in their standard state or reference state. Therefore, the second point of your definition is also validated. Hence, we can say that our given equation simply represents the standard enthalpy of formation. And therefore, we can also say that for this reaction, the standard enthalpy of reaction will be equals to the standard enthalpy of formation. And we will look on to its logic in the upcoming slides. Suppose we take one more example, which is formation of methane. So can we call it as the standard enthalpy of formation for the given equation? Yes, because 1 mole of methane is formed, and it is formed from its constituent element which are present in the reference state. So carbon is present in the graphite and not any other allotrope, whereas your hydrogen is present in the molecular form. Therefore, this reaction represents the standard enthalpy of formation delta FH naught. Let us move to a different example, which is dissociation of calcium oxide. No, sorry, not dissociation. The reaction of calcium oxide and carbon dioxide to form the calcium carbonate. Now, is this reaction a standard enthalpy of formation? No. So, if you consider the enthalpy of reaction for this condition, then it will be not equal to the standard enthalpy of formation. What is the reason? Let's see. So, if this case, if you consider the formation of calcium carbonate, then it is not formed from calcium, carbon and oxygen in the reference state. We are not seeing any O2 on the left hand side, any carbon, graphite on the left hand side, or calcium salt in the left hand side. Therefore, this is not the standard enthalpy of formation. I hope now it is clear to you that why I am not calling this reaction's enthalpy as the standard enthalpy of formation, because the calcium, carbon and oxygen are not in their standard state. Then we can consider one more example. In this case also, if you look, then the enthalpy of reaction is not equals to the standard enthalpy of formation. You can think about its reason. Meanwhile, I will tell you, just think about it. It's very simple. So the reason is that instead of the formation of 1 mole, we are getting the formation of 2 moles in this given reaction, right? So in this case, we can say that the standard enthalpy of reaction is not equals to the standard enthalpy of formation. But the question arises, can we convert it? Is it possible for this one? Yes. In case if you are not getting 1 mole and the reactants are present in their standard state or reference state, then in that case, you can take the numerical calculation for the conversion of your enthalpy of reaction to delta H formation. Okay, so this is only applicable if your reactants are present in the reference state. And you can see that water and bromine are present in gases and liquid respectively, which are their standard states. So to convert this enthalpy of reaction into formation, we will simply multiply the standard enthalpy of reaction with 0.5 or divided by 2. Why are we doing it? Why we are dividing it with a coefficient of 2? Because if you divide it, you will get your final equation as half H2 plus half Br2 gives us HBr. So we got now 1 HBr. You will apply the same algebraic thing to the enthalpy of reaction. We will get it as minus 36.4 kilojoule per mole. Here, got it? So it's very, very important to understand that how you can convert it. Now the question arises, why are we dividing it? Is there any logic behind it? About this thing, we'll see when we will discuss the thermochemical equation. For now, you can simply take the thermochemical equation as your what? Simple algebraic calculation. Now, can we use the standard enthalpy of formation for the calculation of reaction enthalpy? Is it possible? Yes, it is possible. Suppose the formula goes as delta H formation from products minus delta H formation for reactants in the standard condition, and that will give you your reaction enthalpy. So this is the formula. Now why I am telling it you to suppose, because you can apply this formula in the previous section. And from there you can easily say that why the reaction enthalpy was equals to the enthalpy of the formation. Suppose we take this reaction. Okay, when we don't know the enthalpy of formation. Okay, or we don't know the enthalpy of reaction. Any one variable is there, then we don't know. How do we calculate it? It's very simple. So we simply take the formation for carbon dioxide, add it with the calcium oxide, and subtract it from the reactant, which is calcium carbonate. Okay, so standard enthalpy of, can say, product minus standard enthalpy of the reactant. If you use the values here, then what you will get? You will get your delta H as 178.3 kilojoule per mole. Right? Now this is true for the reverse reaction. Why? Because we are not taking the product, we are taking the reactants here. You can see it. The reactants are present here. So we got the answer in positive value, which is just opposite of this. Why I am writing it so? Because you can see that how on reversing the reaction, you can get the opposite value. We will see the same in the thermochemical equation. When you will see the convention, there you will observe that whenever we reverse the reaction, we get an opposite sign. Got it? Now, the point is that what is happening if you are taking the formation of a given compound from its reference state. In that case, what will happen? The reactant are present in the reference state, therefore, their standard enthalpy of formation will be taken as 0. And the standard enthalpy of reaction will be simply equals to the standard enthalpy of formation of the reactant of the product. Okay, so that is the reason when we take the reactants in the reference state, we get the enthalpy of reaction as standard enthalpy of formation for the product. Got it? Now let us move to a very, very important topic, which is thermochemical equation. You have encountered this equation to and fro in the previous sections. So let us try to understand it with the help of its definition and few important conventions. So what is a thermochemical equation? It is a balanced chemical equation written along with the enthalpy change of the reaction. How? By specifying the physical state and allotropic state as well. So if you see, go back and see, you will see that the carbon, if you is being mentioned along with the state which is solid and along with the allotropic form which is graphite. Okay, so you have to mention the allotrop as well as the physical state. Now, in most of the cases, the allotropes are not possible because carbon has a distinct property of showing the allotropic state. You will not notice this for each of the element or compound, but the physical state is true for all of them. Let us take an example. Suppose we are seeing here the combustion of ethanol. What we can see, first of all, the equation is completely balanced. We have 2 carbons on the left hand side, 2 carbons on the right hand side, 5 hydrogens, the left hand side. Again, how many hydrogens are present on the right hand side? 6. Okay, so we have one more hydrogen on the left hand side after O. So we have 6 hydrogens on both sides. What about oxygen? So 3 to just 6 from the molecular oxygen and 1 from the ethanol. So 6 plus 1, 7. Similarly, on the right hand side, we have 2 to the 4 from carbon dioxide and 3 from water. So 7 oxygens are present here. In this case, the enthalpy change for the reaction is also mentioned, which is minus 1367 kilojoule per mole. Therefore, our given equation is a thermochemical equation. Okay, one more point. What is it? It is your physical state. So you can see the ethanol physical state is mentioned, liquid. Oxygen's liquid state is mentioned as gas. Carbon dioxide also is present as gas, and water is present as liquid. So states are also mentioned. Do we need to specify the allotropic state? No. Our given elements have no allotropic form. Therefore, we do not need to specify the allotropic form. Here, the negative sign that you are seeing indicates that the reaction is a exothermic one. Now let us move on to the conventions that we use while writing the thermochemical equation. First is, if you are talking about the coefficient in a balanced thermochemical equation, then they are about number of moles. Okay. From the first chapter, if you see, the coefficient we are defining the molecules, ions, everything, right? But in this case, it is specified only for the number of moles, both for the reactants and products. Second thing, the enthalpy of reaction has a unit of kilojoule per mole. So it is defined for per mole of the reaction and in terms of kilojoule. What is the third thing? That the value of enthalpy change for a given reaction has a reverse sign if you reverse the chemical equation, and we have seen illustration of this in the calcium carbonate example. Now, let us try to understand the same with some points. The first was numerical coefficient in chemical equation. What do they define? They define the number of moles and not the number of molecules of reactants and products. Got it? Then this is applied for both reactants and products, and it is an essential stoichiometric significance that you should remember for a thermochemical equation. What was the second convention? The second convention was that the delta RH naught, which is standard enthalpy change, and the molar reference. So, if you are writing it as standard case, then you have to define it for a per mole condition. Therefore, you are keeping the coefficient indication as moles and not as molecules, because we are writing the enthalpy change in terms of per mole. And we have seen it that its representation is kilojoule per mole. What was the last convention? The last convention was about reversing the sign. Okay, before moving on, let us see one more example. Suppose you are seeing the iron oxide, which is reacting with hydrogen to give us iron and water. Then, in this case, your delta RH 1 naught is minus 33.29 kilojoule for per mole. Let us just specify, or you can say modify the reaction. What will happen? We will change the coefficient. If you change the coefficient of this reaction by dividing the whole thing by 2, what will happen to the enthalpy change? The same algebraic thing will be applied to the enthalpy change as well. Now it will be minus 33.29 by 2, which is minus 16.645 kilojoule per mole. So what is being seen here? That if you are changing the coefficient of your chemical equation, you will also see a change in the enthalpy of reaction. So we can say for this reaction that delta RH1 naught divided by 2 is equals to the delta RH2 naught. Okay. Moving on further, the last one was that the value of delta RH naught is having a reverse sign upon reversing the chemical equation. Can we define it? Yes. Let us take an example. Suppose we are seeing the formation of ammonia. So it is your Haber's process and nitrogen or hydrogen are reacting. And in this case, you are getting a negative value for the enthalpy change of the given reaction, which is minus 91.8 kilojoule per mole. Now what we do? We reverse the equation. And when we reverse it, what will happen? The value will be now in positive, but the magnitude will remain same, which is plus 91.8 kilojoule per mole. What is the process? It is not the formation, it is the decomposition of ammonia. Okay, now we got the thermochemical equation and we will move on to the last topic, which is Hess's law of constant summation, constant heat summation, right? So this principle is very, very important for a thermochemical equation, and in most of your questions, you will observe the implication of this principle, right? So what is Hess's law? It says that if you are doing a multi-step reaction, okay, then if you want to calculate the enthalpy change for the overall reaction, you will simply add the enthalpy change for each step individually. Why we are able to add it? Because enthalpy change is an extensive property and extensive properties are additive in nature. But an important condition, if you are doing this reaction, your temperature should remain same. It should not change throughout the process. How can we represent it mathematically? So suppose your reaction is going to n number of steps whose enthalpy change is delta RH1 naught, 2 naught, 3 naught up till n naught. Then the overall enthalpy change can be written as a summation of all of this, and that will be equal to the enthalpy change of the overall reaction represented by delta RH naught. Now what is the use of it? It helps us to calculate the enthalpy change for those reactions whose enthalpy change cannot be reduced directly. Okay, so we cannot observe the amount of heat exchange that is occurring in some reactions due to the challenges of the reaction, and for that case, we use this Hess's law of constant summation. Now remember, this is just the approximation and not the exact value. You can get some deviations, obviously. Suppose if you take the case of graphite conversion to carbon monoxide and you don't know the delta RH naught for the given reaction. How do we calculate it? So for that, you need to know that there are some other information that are available to you. Okay. Now, why the calculation of enthalpy change is difficult in this case? Because generally, whenever you do the conversion of carbon to carbon monoxide with oxygen, you don't get it. You directly get it converted into carbon dioxide rather than carbon monoxide. So for this reason, we need to modify some equations so that we can get the enthalpy change for our graphite conversion to carbon monoxide. Okay. So let us find some ways. To do this, we will use the Hess's law of constant summation. But apart from this, we will need some informations also. Like if our target reaction is conversion of graphite to carbon monoxide, then we will need two reactions probably. First is the conversion of carbon to the carbon dioxide, which is generally observed, and its enthalpy change is minus 393.5 kilojoule per mole. Then we need a second reaction, which is oxidation of carbon monoxide to carbon dioxide through combustion. Now it is observed that the enthalpy change for this second equation is minus 283.0 kilojoule per mole. But if you look at our target equation, we only need the carbon, graphite, we need oxygen, yes, but we don't require carbon dioxide, and we need carbon monoxide on the right hand side, that is on the reactant side. But if you look at the equation number 2, we have carbon monoxide on the left hand side. So we need to reverse it. But why we do not need to reverse the first equation? Because carbon graphite is already present on the reactant side. Okay, so we do not need to do anything with that equation. And it is also already present in the required amount of stoichiometric coefficient. It has a stoichiometry of 1. So what we will do in the next step, we will reverse the reaction number second. If you do so, what will happen to the reaction enthalpy? It will take the opposite sign. Now, the carbon dioxide will be decomposed to carbon monoxide and half mole of oxygen, and the enthalpy change of the reaction is plus 283.0 kilojoule per mole. Okay, now we have two equations, equation number third and equation number first. 2 is been reversed to the third for according to our requirements. Now we will add equation 1 and third. If you will add equation 1 and third, you will get your target reaction. And you will add the enthalpies as well. How? So this was the first equation, this conversion of graphite to carbon dioxide and the decomposition of carbon dioxide to carbon monoxide and oxygen. If you add both of these equations, what you will get? You will get your desired equation, which is graphite carbon getting converted to carbon monoxide. What about the enthalpy change? You will add 283.0 plus minus 393 kilojoule per mole. So it is a simple subtraction. You will do it and you will get your value of enthalpy change for the conversion of carbon to carbon monoxide as minus 110.5 kilojoule per mole. Now, moving on further, there is another thing which we can do to understand the Hess's law of constant heat summation. What we can do, we can represent it pictorially. Let us take an example, hypothetical reaction where A is going to B and it is going to one route, right? So we are specifying a route through which the conversion is taking place directly from A to B. Can we do the same with a different route? Yes, it is possible. How? Suppose we go through a different route in which we are doing 3 steps. And for those 3 steps, our reaction enthalpy is delta RH1, delta RH2 and delta RH3. This can be represented pictorially as this diagram. You can see A is going to B directly and the enthalpy change of reaction is represented as delta RH. Whereas in the second process, if you see, we are going from A to C, C to D and then D to B. And the enthalpy change involved in those processes are respectively delta H1, delta RH2 and delta RH3. So for the overall reaction, we can write delta RH is equals to delta RH1 plus delta RH2 plus delta RH3. Now, let us summarize all of this. How we can summarize it? So heat change during a reaction is called as the reaction enthalpy. Second thing what we studied, that the standard enthalpy of reaction is nothing but the enthalpy of reaction at standard states. Third thing is, we can also have enthalpy change during a phase transformation. For example, for conversion of solid to gas to liquid, we have a standard enthalpy of fusion. For the conversion of liquid to gas, we have standard enthalpy of vaporization. And from solid to gas, we have standard enthalpy of sublimation. All of these processes that you are seeing are endothermic. So they will need heat for the conversion. What next we did? Next we studied about the standard enthalpy of formation. What is standard enthalpy of formation? It is the formation of the compound or the substance from its element, where the elements are formed in the most stable state or in the most reference state. And for the reference state, you will take the elements delta FH naught as 0. How do we calculate the enthalpy of reaction? In terms of the standard enthalpy of formation, we simply subtract the enthalpy of formation of product minus the enthalpy of formation of reactant. After that, we get to know about the thermochemical equation. So basically, it is a balanced chemical equation along with the enthalpy change related to that reaction. How can we reverse a reaction? What are the conventions that we saw? So we can reverse it by reversing the sign of delta H. Next, what we studied, the Hess's law, which says that if you are doing a reaction in multiple steps, then for the overall reaction, you can simply add the enthalpy change for the individual steps to get the overall enthalpy change for the reaction. And it's very important for those reactions in which we cannot directly calculate the enthalpy. So this was all for today's class. I hope you enjoyed the session. Thank you.